In this video, we're going to briefly introduce the concept of a vector and some notation that goes along with it, as well as some of the simpler geometric and algebraic properties of vectors. And if you ask someone like, what is a vector? Depending on who you ask, you might get quite the varied set of responses. And I guess in the most simplest of terms, we could say that a vector is a, a quantity or an object. So a quantity with both magnitude and direction. So magnitude and direction, right? And this is important because in a lot of the physical sciences, you deal with lots of quantities that have both magnitude and direction. So vectors are a good way to sort of describe such a quantity. Now, geometrically, so let's start with the geometric way of thinking about vectors. So geometrically, a vector is a directed line segment. Right, so we know what a line segment is, and we should have an idea of what it means for something to be directed. So, what do they look like? Well, let's start with the line segment. To have a line segment, you have to have two distinct points, right? Meaning that the points are different. I'll just call this point A, call this point B, and of course you have a line connected them. So that's the line segment part. So up right now at this point, this is not a vector. If I now attach a certain direction to this, so for instance, if I put an arrowhead there, then suddenly that's what we call a vector. The point where the line segment starts, this is sometimes referred to as the tail, or more formally the initial point of the vector. So this is the initial point right there. And then this would be the terminal point of the vector, often called the head. So you might hear some people refer to like the head of a vector or the tail of a vector. The tail is referring to the point where the vector starts, and the head is where the vector ends, right? So that's kind of the geometric way of representing a vector. Now, what about the algebraic way? Well, for the algebraic way, we need a coordinate system. So we can't just kind of arbitrarily put this down and not say a little bit more. So we need a coordinate system that tells us, okay, what is the space in which these points exist? So is it just one space? Is it two space? Is it three space? So algebraically, and this is really what we want to get to, but the geometry is a nice place to start. Algebraically, we need a coordinate system to describe a vector. Right, and we happen to know such, in fact, we have several systems now. So let's start with R2. So they're two-dimensional coordinate systems. So in R2, and what I'll do, I'll use a specific example here. And let's say we have something like this, just 3 hash marks there, each 1 unit. And just for convenience, I am going to have the initial point of the vector be at the origin, and then let's say the terminal point is at the point 3, 2. So my vector goes here, and I'll call this O for origin, and then let's call this A for point A. Now let's talk about some notation first. So one way to denote a vector is to use the literal initial and terminal points. So take OA, you put a line above it to indicate that it's a line segment, but then to give it a direction now, you make that line like have a little harpoon. So I'll call just this line above with the little arrow or hook there, just call it a harpoon. So this is interpreted as the vector going from initial point O, in this case the origin, to point A. All other an alternative notation is to use a lowercase letter to represent the vector. And if you read a textbook, for instance, it will have that lowercase letter written in bold. Well, I can't write in bold, so what I'm going to do is I could call this v for vector, but to indicate that it's really a vector, you put the same kind of harpoon on top. So you can do it like that. Right? Now let's see if we can describe this directed line segment with numbers. Well, if you think about what this vector does, it starts at the origin and then it goes to the point 3, 2. Now you can think of that motion in two stages. The first stage, for instance, you could say, well, you go 3 units in the positive x direction, right? So you could think of it going this way. So you go here first, right? And then that takes you from 0, 0 to 3, 0. And then to get to the final point now, the terminal point of the vector, you go 2 units in the positive y direction. So you go up this way, right? So you go 3 to the right, 2 up. And what we can do is we can use this, essentially this change in x and this change in y, we can use it to define what this vector does or what this vector represents. And the way we do it is to distinguish between a point and a vector, we're going to use angled brackets. And since this is a two-dimensional vector, we're going to have a pair of numbers in here. And the first of the pair will represent the change in x, which in this case is a positive 3. And then the second number in the pair will be the change in the y, which in this case is a positive 2, right? So over here we have the geometric way of representing the vector, with our directed line segment. And then over here now, this is the algebraic way, and this is called the component form of the vector, right? So this is called the component form of the vector, right? So the component form of vector v, right? And we refer to the 3 here is the x component as opposed to coordinate, right? So we're trying to distinguish between a point and a vector, and then the 2 would be the y component, right? And a lot of work that we will do with vectors will be very easily done once we can get it in that component form. All right, so that's what it looks like in R2. In R3, it's going to be the same idea, right? It's the same idea. We have our coordinate system for R3. We're going to, again, continue to use that right hand orientation, where we have our x, our y, and our z. And if we do something similar, again, I'm not going to use really large numbers just because it's harder to sketch. But let's say we have the vector 1, 2, 3. So what would happen is, and again, I'm going to start, just for convenience, let's say we start at the initial point at the origin, and then so we will go, think of it, if we're doing the vector 1, 2, 3, we'll go 1 in the positive x direction, and then 2 in the positive y direction, and then 2 in the 3, sorry, I need to go up, actually 3 in the positive z direction. So this would be the vector and then let me call this O and A. So again, it would now have a component form in R3 of 1, comma 2, comma 3, right? So the nice thing about a vector, it again in the sense that it remember what a vector is. It's a quantity that has magnitude and direction, and the components will essentially tell you the components of the vector describe both of those two things, right? Now, as far as the magnitude is concerned, the magnitude is going to be like how long the vector is, right? And in a bit, we'll take a look at the the formula for the magnitude of a vector, right? And of course, the direction is defined by that arrow, right? So the component form, really helpful to have. So let's just say this. So in general, um, uh, v equals, and let me just say x1, y1, right, is the component form of a vector in R2, and v equals x1, y1, z1 is the component form of a vector in R3. Now, in both cases, I drew the vectors with the initial point at the origin. But what if the vector isn't drawn at the with the initial point at the origin? In fact, let me show you something. So let's say I just drew this, right? And I didn't tell you if this was in 2 dimensions or 3 dimensions. You wouldn't know, right? If I didn't really set the context, you wouldn't know. I'm going to copy this, and then I'm just going to paste this vector, the exact same vector, all over my board, right? And let's do another one here just for kicks. There we go. So I basically took my vector v and I just essentially duplicated it everywhere. The exact same length, the exact same magnitude. But they all have different initial points, right? So the thing is, since they're essentially the same, we come to the realization that the initial point, right, of the vector, it doesn't really matter. What matters is how long the vector is and what direction the vector is in. So all of these that I have here, these are considered equivalent vectors. They're all the same vector v, right? So geometrically, equivalent vectors in the sense that they have the same magnitude, same direction, right? But since that magnitude and direction is embodied in the component form, in other words, having the components, right, of the vectors, right? Like how much is the change in the x or the y and the z, since that defines the magnitude and the direction, another way to say that two vectors are equivalent is that if they have the same component form, right? So two vectors are equivalent if and only if their components are equal. So their components are equal. Right? So again, as far geometrically, they don't have to have the same initial point to be considered equivalent, but algebraically, their components would have to be the same. All right. Now, once we have vectors, the question is, well, what can we do with them, right? Well, what we're going to do is just briefly describe some of the simple arithmetic operations you can do with vectors, right? So the two, I would say, basic arithmetic operations related to vectors are, so what can you do with them simply? Well, you can add them. So you have vector addition, right? And scalar multiplication. Now, what do we mean by scalar? Well, scalar is the word that we're going to use to distinguish between just a number versus a vector. So vector addition is referring to the operation of adding two vectors together. Scalar multiplication is the operation that involves multiplying a vector by a scalar, right? And what I'm going to do is I'm going to write down these operations for vectors in R3, with the understanding that in R2 we would just essentially delete the third component of the vector. So if, let's say u is the vector u1, u2, u3, and again, to distinguish that this is the vector, we're going to put the harpoon on top. So if that's u, and v is the vector v1, v2, v3, then here is vector addition. So if I wanted to add these two together, so we're going to use our same notation for addition, and we basically add the corresponding components. So you take the first component of u, add the first component of v, so u1 plus v1. Then you take the second component of u, add the second component of v, so u2 plus v2. And then finally, take the third component of u and add the third component of v. So u3 plus v3, right? And notice we add two three-dimensional vectors together, we're going to get a third three-dimensional vector, right? So that's the vector addition. And then for scalar multiplication, then and I'll use k as my scalar. So if k is my real number, then k times u, meaning I'm going to take the vector u and multiply it by the scalar, is formed by multiplying each of the components of u by that scalar. So ku1, ku2, ku3, right? And there you go. So these are the two basic vector operations that we can perform, and even though they're stated with three-dimensional vectors, the process is exactly the same for two-dimensional vectors, right? Now you might say, well, what about subtraction? Why don't we define subtraction? Well, technically we don't need to define subtraction, but I'll write it like this. The difference u minus v is computed as follows. So if instead of adding, if we have to subtract, well, this is essentially what you would do. You would add the negative of v to u, right? So this is basically, now even though this is how it's described, in the way we actually compute it is simply by subtracting the corresponding components. But you don't typically see vector subtraction, right, as a as defined the way addition and scalar multiplication is, because we can express the subtraction in terms of addition and scalar multiplication. So this is saying multiply v by -1 and then add u to that result, right? And a lot of the standard properties that we're used to, as far as like the associativity property, the commutativity property, the distributive property, all those properties still hold for vectors. So I'm not going to formally state those. We're just going to assume that those properties hold, and we can do all of our basic algebraic questions. All right, so let's do a quick example just illustrating a lot of these. So let's do an example. And I'm going to, so let u be the vector -2, 0, 1, and v be the vector 3, 5, -4. So let's just go through and compute a couple things. So let's say we wanted to take u plus v, so the simple sum of these two vectors. So by definition, it's going to be -2 plus 3, comma 0 plus 5, comma 1 plus -4. And then that's going to give us the vector 1, 5, -3. Let's say I wanted to multiply through the vector u by the scalar 3. Then all I would do is it will be 3 times -2, comma, 3 times 0, comma, 3 times 1, and then we simplify. So we'll get the vector -6, 0, 3. Right? And then let's say we wanted to do something like v minus 2u. So then we could take our vector v. So I'll do this. So sometimes you can sort of write down more of the intermediate step if that helps you eliminate any arithmetic errors. And then u is -2, 0, 1. And we do the same order of operations, right? So we're going to multiply before we subtract. So we'll have 3, 5, -4, minus, and then in the angled brackets, -4, 0, 1. And then again, what we could do, we could distribute the negative, right, like this is implying, and then add, or we simply just subtract the corresponding components. So in this case, it will be 3 minus -4, comma, 5 minus 0, and then -4 minus 1. So that leaves me with the vector 7, 5, -5, right? So really easy to start with two vectors, and then we can do these operations quite easily. The last thing we're going to end with in this video, I think what we'll do is we'll save the magnitude for the next video. But in this case, I just want to say, well, what do we do if, for instance, the vector doesn't start at the origin? If the initial point is not at the origin, how do we find the component form? So let's say, and what I'm going to do is, so let's say this is our vector, right? And this is P1, and it starts, so this is X1, Y1, and then this is P2, X2, Y2. And I want to find the vector that goes from P1 to P2. I want to write it in component form. Well, here's a trick that we can do. Instead of going directly from P1 to P2, I could take a detour, right? Who doesn't like a good detour? It's adventurous. We could start at P1 and then go to the origin, and then from the origin go to P2. So if I call this O, right? So you notice I would still start and end at the same point, but I would be using two vectors instead of one. So in other words, I would go from here to here, so I would use that vector, and then from the origin to P2 there. Now, going from P1 to the origin would be the opposite of going from the origin to P1. So in fact, let me write out a couple steps here now. So if I want to go from P1 to P2, I can do this. I can go from P1 to the origin and then add to that going from the origin to P2. But here, right, and this is where that multiplying by -1, what it does, it essentially changes the direction of the vector. So I can express this as negative OP1 plus OP2. Now, since both of these, right, start at the origin, right, because I have it going from O to P1 and then O to P2, I can use our previous way of defining the vector in component form and write this one down. So I'll put a negative there, and then in angled brackets, going from O to P1, I would have a x1 as my first component, and then y1 as my second. Let me write that more clearly. So we'll have comma y1, right? So it'd be the negative of that vector plus, and then going from O to P2, which would be the vector x2 comma y2. But now look what we're able to do. We can use our scalar multiplication and addition to simplify this, to write it as a single vector. So this is negative x1 comma negative y1 there, and then plus x2 comma y2. So then when I add these, what I will do is, so this is negative x1 plus x2 comma negative y1, negative y1 and then plus y2. And then since our components here are real numbers, what I can do is I can write this as x2 minus x1 comma y2 minus y1. And this is the kind of really useful formula for finding the component form of a vector where the initial point is not at the origin. And notice what happens. Since the vector goes from, again, think of it in two stages. Let me do the two stages here. Your x1 increases to x2. So this change right here is x2 minus x1, the larger x minus the smaller x. And then the change in y going up now would be, again, your final y, which is y2, minus the initial y, which is your y1. So again, you can see the change. It's just that the change now is not relative to the origin, but relative to another point. But basically, just taking those differences will give us the component form. And similarly, this holds in R3. So similarly, so I'm not going to sketch it, I'm just going to state it. So similarly, if P1 is the point x1, y1, z1, and P2 is the point x2, y2, z2. If these are points in R3, then we can write down the component form of the vector going from P1 to P2. Here are the components. It's the difference in the x values, so it's x2 minus x1, comma, the difference in the y values, so y2 minus y1, and then the difference in the z's, so z2 minus z1, right? And let's just do I'll just do a really quick example of this, right? So let's say P1 is 2, negative 8, 3, and P2, or second point or terminal point, is 4, 0, negative 6, right? In fact, let's write down two vectors. Let's write down the vector that goes from P1 to P2. So P1 to P2, that has components 4 minus 2, right? Basically the head minus tail, and then 0 minus negative 8, and then negative 6 minus 3. And that gives us 2, 9, negative 9. Oh, not 9, this is 8. The y component there is 8. Right? And then if I wanted to do the vector that goes from P2 to P1, there are two ways I could think about it. I could do the same difference, but then just realize that this vector is the opposite of this vector. So this is the negative of P1 to P2, and then that's the vector negative 2, negative 8, 9. And all I have to do is essentially look at this vector and multiply it by negative 1. All right? So I think that's really kind of that's a good intro to vectors, and some of you may have seen all of this before, but again, it's not something that I want to assume, so I want to make sure that we have this, kind of foundation. I keep saying that we have this foundation upon which we're going to build some interesting mathematics. So that's it for vectors, and in the next video we'll take a look at the magnitude of a vector. See you then.